All right, let's start talking then. Yeah, everything is good. So, hi Azalia, thanks for joining us. Towards this is great to have you. I was listening to your talk, but I am not the most expert when it comes to deep learning stuff, so you'll have to kind of excuse me when it comes to like a lot of the specifics. But we're still very excited to have you. So thanks again.
Yeah, of course, happy to be here.
Great. So why don't we just get started with like your professional background? So can you tell us a little bit about yourself?
Yes. So I got my bachelor in electrical engineering from Sharif University in Tehran in Iran. And then right after that, I came to Rice University, where I got my master's and my PhD in electrical and computer engineering. And back there, what I was working on was doing algorithmic and hardware software co-design for machine learning, for large-scale data analytics model and machine learning, with a focus on more traditional machine learning algorithms. But towards the end of my PhD, when deep learning took off, I switched to deep learning. Afterwards, I was looking into an academic job market. I wanted to be a professor, but at the same time, I was really interested in deep learning research, and to kind of learn more about that domain, I very accidentally saw a flyer for Google Brain residency program, where the goal was people with other backgrounds other than deep learning or machine learning can also apply and become researchers in deep learning and machine learning. So I kind of thought of it as like a postdoc for myself, where I go there and become more of a deep learning researcher, and then apply for faculty jobs in a year. But I ended up staying there forever, at least right now. I've been there for 3.5 years, and I'm very happy there, and kind of try to bring my background in like software, hardware, co-design optimization into my new role as a researcher at Google Brain. And I can continue from here.
Yeah, okay. Please go on.
So something I noticed in the machine learning community, like that is very common, is that a lot of people are very excited about research in computer vision, in speech, in NLP, robotics, and games. Those are all very exciting applications to us humans, right? If we can generate a new face of a human or a cat, that's much more exciting than, let's say, if you design a new computer, right? We don't connect with those as humans, with those kind of domains or fields, such as computers or systems or hardware. So I was very excited into doing machine learning for systems and computer design, because those are basically, systems and computer design are the biggest enablers of machine learning. Like a lot of success of deep learning is because of the better hardware and better systems that we have right now that we didn't have like 10 years ago.
Can you give us an example of some of the systems that have developed that have enabled stuff like deep learning?
Of course, like these are the systems such as TensorFlow, such as PyTorch, that it's very common, it's very powerful. Everybody can easily get into training their own models in deep learning models in those frameworks. The other important aspects are the chips and the hardware, like GPUs, originally designed for games, but now like machine learning and deep learning is one of biggest GPU customers are deep learning people, researchers and
Bitcoin,
users, right? And Bitcoin. But TPUs, like Google has its own TPUs or tensor processing units, a really powerful hardware to run machine learning algorithms that we didn't have before. So it's kind of like these hardware, new type of hardware and system enable machine learning and deep learning to be what it is today. And in my talk earlier, I was referring to this graph by OpenAI, that they analyzed these deep learning models, and they realized that since 2012, the amount of computational power used in the largest AI runs has doubled every 3.4 months. And by comparison, Moore's law had an 18-month doubling period. So it means that we really need like significantly better computer hardware to be able to keep up with the computational demands of AI. So the way I think about it is that why not use machine learning itself to help AI and design the next generation of systems and chips with machine learning, so we can quickly iterate and design better chips and systems and use them to develop better AI algorithms. And
right. I mean, is that something that you are mainly focused on at Google Brain, where you focus more on the infrastructure side, like as you mentioned, chips, optimization? Are those your primary roles?
So my main role is to do research that enables, say, designing and optimizing systems and hardware. And the type of research I focus on, a lot of it is focused on deep reinforcement learning algorithms as kind of like sequential decision-making optimization methods that can really enable us to design and optimize systems. So my research is on deep reinforcement learning at the moment.
No, that's very cool. Actually, so for those who might not be familiar, what is a sequential decision-making process?
So to give you an example, let's say we want to, let's say in a robotics task, a robot wants to get to a target and the robot is located on a 2D grid and wants to move around. The sequence of decisions are decisions about where the robot moves first. Does it move right first, left, right, and straight ahead? Because there could be like barriers in front of the robot, right? So there are a series of decisions that you take in sequence. You take one action, which is go right, and then you take the next action. Your actions are kind of conditioned on the previous actions that you have taken. Your end goal is to take these series of actions such that, for example, you reach the target as fast as possible with minimum number of moves. So a sequential decision-making task has to do with how you can optimize this series of decisions such that you get to your target reward function, whatever that is, in an optimized way.
Can you tell us how this optimization itself happens in that process?
So, yes, I can tell you about how this optimization, for example, in the context of policy optimization or reinforcement learning, how it happens. You can imagine you have a model, a neural network model, that kind of, this model represents your policy. In the beginning, this model is initialized with random weights. It doesn't know anything about your environment. But gradually, what this model does is that take the current state of your problem. For example, the robot is here, here is your 2D grid, here is your target. Take some representation of your input state. It outputs a distribution or a probability distribution over the actions that you have. Let's say you have 4 actions, move up, down, left, or right. It outputs a probability of with what probability you take which action, right? In the beginning, it's random, so this probability is just random in the beginning. But let's say it generates some distribution, you sample from that, or you take the argmax, and then you take that action, and you look into how much you progress, like a reward function. For example, how closer you got to your target. That kind of can be taken as a form of your reward function, right? This is a reward function that now, and then you go ahead. You have this intermediate reward function, and you take the next action, and all the way until you reach your target, or you don't, right? In the end, you have, after a fixed set of, let's say you go through a fixed set of iterations of taking these actions, you have a reward function, whether you got to the target or not, right? So the collection of intermediate reward function and the end one can then be used as a feedback to go back and update the parameters of this neural net that represent your policy. Now, there are many different ways of how to use this reward function, but the beauty of it is that this reward function is something very abstract. It's like 1 or 0, for example, if you reach the target or not. But then somehow you can take it back and make it a differentiable, like relate it to the differentiable parameters of your neural network. For example, using the reinforced equation or other methods which are, or other like reinforcement learning. With a lot of reinforcement learning approaches that kind of approximate that. Then you update your parameters of your policy and you start the game.
I'm a little confused on terms myself. So when you say policy, we're not talking about like public policy, right?
No, the policy, yes, here the policy is your reinforcement learning model. The reason it's a policy is that it takes an input state and it takes set of actions. It predicts an action given a state. That's why we call it a policy.
I'm still a little bit struggling to understand the optimization bit. So when it's like, let's say, supervised learning, as you mentioned, there are labels, and you can use whatever metrics that you're using for a particular business goal or whatever it is, to which you can optimize, right? Mm-hmm. When it comes to reinforcement learning, where you say that there are no labels, how can we find, say, parameters for tuning, whatever it is, to get from one end to the other end in the most optimal way?
Okay, so yes, like you mentioned, there are no labels here, but we still have a reward function, for example, right? We still have a state of the input of the problem, and in the end, we want to optimize the reward function. So in a lot of this policy optimization algorithm, what we are doing is we are training a policy that optimizes the expected reward function given the distribution of actions that it predicts for a given state. So the policy, if you sample from this policy, there are different actions that it predicts at different time. You sample action 1, you sample action 2, and then there is like, you have a trajectory from the beginning to the end, and then you have a reward function. This trajectory from the beginning to the end is like one series of sample from your policy. Mm-hmm. That is like, and with certain probability, right? Because each action is taken with a certain probability. And then these probabilities are cascaded together, and then you have a reward function. So you can think of it as we are, instead of optimizing, finding a set of actions or a series of actions that gives us the optimal reward function, we are optimizing it towards a set of actions that optimizes the expected reward function given the probability of actions that come from this policy. So that's kind of a different way of thinking about this problem.
I see.
How it's different from a very clear supervised
I see.
problem.
I want to switch gears a little bit because I'm really fascinated by this other work that you've been working on, which is, if I'm getting this right, sparsely gated MOE, the mixture of experts layer,
yes.
if I'm getting that correct. So can you tell us a little bit about this particular layer?
Yes, this was one of the first projects that I did when I joined Google Brain with a group of excellent colleagues, and the idea behind this layer is that if you look into the deep learning model, like convolutions, transformer, LSTMs, like a lot of those are relatively dense, meaning that an input example, like an input data set, goes through all of the network from the beginning towards the end, right? We usually process each input with the same amount of computation across all the input examples. So the idea behind this work was that we can have a union of experts, that each expert is represented by a neural network itself. And these experts can be specialized in different types of data within your training data set. So as you're passing an example throughout the model, the example goes through certain paths through this neural network and goes all the way to the end, but not through everything. There are many advantages to this model. First, we can have models with a lot of capacity that can learn from massive data, meaning we can have a lot of parameters. In one of the models, we had billions of parameters that we could train billions of data point on it. But the beauty of it is that it's in simplicity, right? Because an example only sees a very small portion of the model, because, for example, we could have 1,024 experts, and an example goes through only like 4 of the experts or only 8 of the experts. So we have this large capacity model, but the amount of computing power applied to each example is still very small. Yet this big model can collectively learn from this large amount of data that we have, and with the large amount of parameters that it can use to kind of encode the knowledge and use for training the model.
So if I'm getting this correct, and feel free to correct me if I'm wrong. So you have this layer that's integrated with a sort of a global model, and in this layer you have a whole bunch, thousands, whatever it is, of these experts, which are neural networks that are investigating different parts of the data, correct? But I guess why yours is called sparsely gated is because we're not looking at a whole, let's say 1,028 experts. You're only going through a few, but then you're still able to arrive at similar results as using all of the different experts. Am I getting close?
Yes.
Or better? Wow.
Yes. So the reason it's named sparsely gated mixture of experts because we train a gate, what we call the gator, that together with these experts, the input to the expert layer goes to the gator first, and the gator decides which experts should process this input. So a sparse number of those experts, or only a sparse number, receive this any input to this gator. So the gator kind of routes the input examples through a few number of experts, and that's why it's called sparse gator. And yes, we have this expert layer together with the gator. We can embed that between an architecture in that paper into an LSTM, like a sequence-to-sequence model. And surprisingly, we could not only get results faster or achieve to the same accuracy as our baseline faster, we could also achieve better results. And part of it was because we could process more data, and the other part of it was because of the regularization effects of this sparse mixture of expert that made the model generalize better to the unseen test data.
Can you go a little bit more in depth about the second part, about the regularization?
Yes. So basically, dropout is a way of doing regularization, and you can think of the mixture of expert as also as in some sense similar to dropout, except that it's it is used in a more structured way, that we actually are using the benefit of sparsity here for computational efficiency as well. So we have all of these models. Each time the gator looks into the whatever activation it got for an example, and then passes it to a sparse number of models, right? Whereas in a dense layer, you see all of the model go through that. So this sparsity is kind of helping with the regularization and making it more robust. Kind of like how dropout drops certain parts of the network. Here we are dropping by design a large number of experts, and then using that for optimization, both computational efficiency and also making the model more robust and generalizable.
What's also very exciting when I was reading your paper on this topic is that you guys are solving this problem that the conditional computation was trying to solve. So can I get some info on this? First of all, what exactly is, am I getting this conditional computation, and sort of the importance of your work in that aspect?
Yes. Again, the reason this is a conditional computation is that despite most other deep learning models where an input goes through all of the network, here we condition an input through a gator model that we learn jointly with the rest of the network. We condition it through the gator and restrict it to certain paths within the neural network, right? So that way, our experts or modules, in a way, they're becoming specialized in different parts of your training data, and also that helps them to become better at processing them and evaluating the data, right? Because we have a lot of data, but each subset of the experts becoming specialized in a subset of this massive amount of data set, because they're conditioned to see only those subsets. So they become specialized in that, but at the same time, the rest of the network is all connected, and the rest of the network sees all of the data. So together with the non-expert layers, they have both a good, like, zoomed-in view of the specialized, the data they're specialized in, and also the zoomed-out version of all the data that they can see, and they can get the best of both worlds and do better in analyzing them.
That's very cool. I want to switch gears one more time and focus more on the Google Brain itself, because I'm very curious. I've never been to that organization, so I'm really curious about what kind of people you get to work with, how your team's structured. Can you give us a little bit about what it's like to work there?
Yes, so I think I've been very fortunate to be at Google Brain for the past 3.5 years. It's a great team. We have a large number of great researchers and engineers that work very well together, and we tackle, we focus on important problems, really hard problems, and it's just a lot of fun working with this team and working on the type of problems that we do. I would say, for a very good extent, we have a very academic culture. We pretty much publish almost all of the research that we do. We are very actively present in terms of publication in all the top tier conferences, so we really encourage our researchers to publish and kind of collaborate with the outside. But at the same time, a lot of the good a lot of exciting work came out of Google Brain. An example of it is Google Translate, which is based on the seek-to-seek and LSTM approach, which is like really amazing, right? They could pretty much revolutionize the way NLP and machine translation is done by using an end-to-end deep learning-based model. So, and a lot of other interesting work that comes out every day, like AutoML is another thing that we are very excited about. And of course, I'm biased. Like, I'm very excited about our work, my team's work on machine learning for systems, and how we can really transform the way systems and hardware design optimization is done with machine learning itself.
Do you get to work with Geoffrey Hinton at all?
Yes, actually my paper on Mixture of Experts was with Geoffrey Hinton, Jeff Dean, and Kwakle. Like, I feel like very lucky to be able to work with them, Sami Benjo. Yes, so I worked with Geoffrey Hinton. He's an amazing person. It's just such a pleasure just to be around him, and the most humble person ever at the same time.
Wow. What is it like working with the man? What is the process like? Is it very like, is he always around when you're doing more of academic stuff? How does that work?
So yes, I would say that I think he's based in Toronto. So I am based in Mountain View, and he sometimes visits, but he's always very open to conversations, to set up meetings, doing brainstorming. He's just amazing, and you don't feel like he doesn't make us feel like, oh, he's like Geoffrey Hinton, right? He's just a colleague and a mentor. The way he of course he's like, we all respect him a ton, and it's so amazing to be around him. But at the same time, he's just so humble and nice to everyone, always there to talk to, brainstorm and such.
That's very cool. We actually have a final question from the TDS community who was very excited to ask you this. So if you can give me a quick sec. So the question is, let's portray two large scenarios. One AI as a tool, and the other AI as a product. Which one do you think is more probable to become the lead scenario in AI? And I guess the question, to me, as I interpret it, has to do with the democratization of AI versus the more corporate use of AI. So, if I'm interpreting this correctly, like, what are your views on this particular topic?
Let me think. I think I'm very positive about AI. I feel like AI is going to help everyone have better lives, and the universe is going to become a better place for AI, and that's going to be for everyone. But at the same time, there are cases where, like in industry, they might have access to more compute and more data, and others might not. But at the same time, I feel like there's a lot of like work and research that can be done even without a lot of data, because you can then innovate around the constraints that you have, and we see that all the time as well, that there are a lot of good work comes out from like academia, right? So I think there are opportunities for both industry and academia to thrive, and in this the era of AI. And at the same time, if we do something great, like for example, if self-driving cars happen, it's going to be, I personally believe that it's going to be great for everyone. It's going to help everyone's life. So maybe they free up some of their time. They can do better in other things. They can innovate. People can innovate in other areas. So I feel like both AI being as a tool or a product or something that is going to help certain people, like, sorry, going back, I feel like it's both, like it's a tool. To some people, it's a product, and it's like, and some people want to be at the forefront of innovating on that. Some other people want to use it as a product to help improve their careers and their lives and different tasks that they do. I feel like all of it is all good, is good for the very most part, and we should really positively think about it and really push forward the frontiers of AI so we can help everybody.
That's exciting. Thank you for that wisdom. So that's actually all the questions I have. Is there anything else you wanted to talk about yourself?
Okay.
If you have anything.
No, I just wanted to thank really my mentors and my colleagues throughout my career and throughout Google Brain, because a lot of times, like, I feel like the path that I had to machine learning and deep learning was a bit different from some other people who had careers in who studied in machine learning specifically to become a machine learning researcher. And so I'm very thankful to my mentors and my colleagues who have helped me throughout the years. And at the same time, I feel like anybody who is interested in AI and doing AI research, I think there's so many available tutorials, classes online, so many different problems that they can take on, like as toy problems. They can have their way into machine learning and then hopefully go from there and do more. So I feel like it's the exciting part about AI is that it's available for anyone who is interested, and anyone who wants can be an AI researcher and a machine learning person.
Right,
so
looking forward to that future. Thank you again, Azalia.
Thank you.
Thank you for joining.